Good morning. My name is Carlos Monarres. I am Business Director of ITENE. Good morning and welcome to this open session of the LIBET project, in which we explain the nanosafety services that ITENE Research Centers offers in the framework of this project. The LIBET project has the support of the European Union Horizon 2020 program, and its main objective is to bring together in the best technology and research centers and leading companies in Europe. To make it happen, LIBET has established an open innovation testbed to accelerate the development and production of the integrated electronic systems. The testbed offers tailor-made solutions for large, medium, and small and startups companies to develop new validated prototypes from the ideas to the concept provided in just 6 months. ITENE has extensive experience in the design of safe process, quantities, assessment, and exposure to nanoparticles in the workplace, and design of means of the protection against nanomaterials, risk assessment under REACH and CLP, and toxicological assessments. In addition, we have more than 15 years of experience in monitoring nanoparticles matters, especially nanoparticles, as well as having low-cost software of measurement systems to allow the creation of the measurement networks obtains data in real time to facilitate decision making. Among the equipment that ITENE has developed, there are a device called nanomonitor, which allows remote monitoring of particles matters, a portable device called nanowatchers that assess the level of exposures to nanoparticles and particles matters in the workplace, and a portable device, the VSafe, the real monitoring of levels, particles, gases, and volatile organic compounds in indoor industrial environments. In addition, we have laboratories in which to evaluate nanoaerosols and produce equipment, carry out toxicological and molecular diagnostic studies, and develop electrochemicals biosensors. Where we are specialized in the REACH regulation on registration, evaluation, authorization, and restriction of chemical substances and mixtures, and we offer consultancy and training services on it. Today, experts from our center in these areas of printing technologies and functional surfaces and safety and environmental monitoring technologies will participate in this session, working together on the safe services that LIBET offers to printed electronics companies that use nanomaterials, nanoparticles manufacturers, formulators of inks, adhesives, and composites based on nanoparticles, and electronic circuit printers with products containing nanoparticles. In particular, screening studies to determine the toxicological profile of the products, studies to assess occupational exposure to nano objects, their aggregates or agglomerates in the workplace, experimental analysis of effectiveness of personal protective equipment and technical risk management measures, definition of safe design methods for reducing of the toxicity and exposures, and advice of the legislation compliance. And sorry for all this test, and I don't want to take any more time, and therefore I will give the floor to my company, to my colleague, Inmaculada Lorente, responsible of the LIBET project at ITENE. I hope that the open session will be very useful for everyone. Thank you very much.
Hello, everybody. Thank you so much, Carlos. So previously to. I'm sorry, but it doesn't work. Okay, previously to start, I want to show you some sample rules that we have in order to the correct operation of this online event. Okay, during the online course, you can send your questions through the chat that you have on the top right hand side of your screen. Okay, also when at the end of the webinar, you can open your microphone in order to ask us the questions and the doubts that you have. When you send your questions through the chat, please indicate your name, surname, and also your company in order to know who you are and who you are answering to. At the end of this presentation, as I said, we have some minutes in order to answer any questions, but if it is not enough time, you can send your questions to evento@itene.com, and we will answer them as far as it is possible. Finally, after the end of this course, you will receive a thank you email with an evaluation in order to allow us improve and continue improving. And we also keep you informed about new events and new courses that could be of interest to you. Perfect. So we now start the webinar. In my presentation, I'm going to introduce you what is the LIBE project and the different services that we offer. Following to me, my colleagues Elena and Arancha will be more focused on the safety services offered inside the LIBE project. LIBE project, as Carlos has said, is an innovation testbed for the development and the production of nanomaterials for lightweight embedded electronics. Here you can find the link. Okay, it works as a single entry point that take companies through these services. We offer different services in LIBE, and we have organized them in 3 different phases: phase 1, 2, and 3. Phase one is a technological and economic modeling. Okay, a brief summary: we evaluate your project, the viability of your project from a technological point of view and also from an economical point of view, in order to see if it is viable or not. In case it is, you can get access to the different services that we provide in this phase. Also, the services that we provide will be described in the next slides. Okay. Also, we offer services in the phase 2. Phase 2 is called pilot projects. So it's where the pilot project is developed. Okay, we have 3 main areas of expertise. One is the development of nanomaterials for printed electronic devices. Also, the formulation pilot lines, where we can formulate inks, adhesives, and composites. And finally, the component pilot lines, where the printed electronic devices are developed by different printing methods and different technologies. The projects that can come to this phase 2 are very different. It can be since a proof of concept in order to see if your product has the qualities needed for printed electronics applications. Also, we work on research and development projects itself in order to increase the TRL of your product or your idea. And finally, we can also work on the prototyping and scalability of your product in order to get a prototype. Then the other services that we offer is comprising phase 3, and they are called knowledge transfer. The main partners that are in the different services, you can see them in the slides. And now I'm going to describe the services offered in phase 1 and also in phase 3. Okay. This is a brief summary of the different services that I'm going to describe. And in phase 1, we offer 6 different services: technical assessment, pre-safety assessment, economic assessment, life cycle assessment, patent mapping, and pilot project financial support. Okay, regarding the technological assessment service, as I said to you, companies can come to LIBEC through a single entry point. Okay, companies go to the single entry point, get access to LIBEC, and LIBEC will send to the companies a document, a user requirement sheet, where the companies have to complete it with all the information regarding their idea, their product, their project, what they are interested in. Okay. This sheet is sent back to LIBEC, and LIBEC evaluate the technical feasibility of this idea, this project, this product, and also the risk level of this development within LIBEC. In case you get an affirmative answer, it means that the project is viable, technological, excuse me, is viable. Okay. In case the project is viable and the technological risk is low, we will send you an affirmative answer, and we can start to work on the different services and on the different phases. Okay, I haven't said it before, but companies can go directly to phase 1, then phase 2, and then phase 3, or if they are not interested in some phases, they can go directly to phase 2 or directly to phase 3. It's not necessary to go to all the phases. Okay, so we give you an answer, and what you get at the end of this service is a description of your idea, how it will be developed, also a table of the risk and some measures in order to solve them. Also, you get a system architecture of how your printed device will be, and also a list of material and components that are needed for this development. The other service that we offer is preliminary safety screening services. Okay, this service will be further described by my colleague Elena and Arantxa, but what we offer here is we give to the companies information about the relevant regulatory and safety information related with your product. Okay, we evaluate possible regulatory applicable aspects about nanomaterial. Also, we evaluate the potential release of these nanoparticles and occupational exposure assessment. And we also take into consideration toxicological and toxicological properties of the materials. Regarding the economic assessment service, as I have said before, when we get the information from your idea, from your project, we make a technological assessment, and we also make an economical assessment. Okay, we evaluate the economic feasibility. The economical feasibility of your product, and also the economical risk level of your idea, of your project. In case we have a high economical risk, we talk with you and see ways and alternatives in order to reduce it. Okay, at the end of this service, what you get is a business model canvas, and also a list of material costs and suppliers benchmarking. The other service that we offer is life cycle assessment. What we offer here is we inform you about the environmental hotspot and potential implications of your product. What we do is an evaluation of the contribution to the climate change. Also, we evaluate the contribution to resource use. We evaluate the expected impacts of your product during the use phase, and also we make an investigation of resource criticality at the end of the life. The other service that we offer is a patent mapping service. It is we offer a review and identification of relevant related patents that are related to your product in order to see the novelty and also the options to protect the development. We make an assessment of competition regarding technology or product. We also make assessment regarding location, geography, and also regarding competitors and potential partners. And finally, the last service that we offer in this phase 1 services is pilot project funding support services. What we offer here is we inform you and we give you a list of possible sources for funding your project. We give you a list of national and international funding options and also a list of contacts of partners of each country for direct consultation. Okay, these are all the services that LIBED offer in phase 1. And now I'm going to describe the services that we offer in phase 3. That are mainly intellectual property rights and patenting services, standardization and safety services, business plan services, and venture capital services. Okay, regarding intellectual property management and also patenting services, what we offer here is seminars in order to teach you and give you an overview of the different options that are available for protecting your results from the project and which one will be the better option for you. We also make an identification of foreground IP, and we also offer a further patent analysis. Regarding standardization and safety, we offer a standardization service, and that means we make a review of standards that are applicable to your printed electronic solution. Regarding the safety service, this service will be also further described by my colleagues in the next slides. But as a brief summary, what we offer are experimental in vitro ecotoxicological studies based on test guidelines and regulatory requirements. We also make a characterization of potential exposure of nano objects, the aggregates and agglomerates, and also we make an identification of occupational exposure scenarios and a definition of proper risk management measures in order to avoid these risks. And finally, the last service that we offer in this phase 3 is funding and investment capital research. We offer here an improvement and optimization of the business plan of your product. We also identify potential investors and also potential funding alternatives in order to give your support you to reach the commercial stage of your product. And also we give you advice on negotiation of terms and the closing of the operation. Okay, these are the different services that are offered in LIBED. And if you are interested in get access to these services or even to get access to the pilot project development phase 2, you can get access through this link. You have to go to LIBED and sign up. Then LIBED will send you a sheet in order to collect all the information that we need to evaluate your project. You have to submit this user requirement sheet back to us and we evaluate it. We will contact you again in 2 weeks in order to see if the project is technological and economical viable. In case it is, we will start to work on the phase 1 or the phase you are interested in. Or if it is not, we will contact you and see possibilities in order to avoid the risk that we have identified. Okay, I hope this information has been interesting for you. And now we are going to present you the pre-safety assessment that is the service offered in phase 1 by ITENE and is going to be presented by my colleague Elena Prima. Thank you so much for your time.
Hello, thank you very much, Irma, for your presentation. As Irma say, I am Elena Prima, working in ITENE, and I would like to explain you the service of that is involved in the phase 1, the pre-safety assessment. First, I would like to thank you for your interest in assist to this open session and organized by in the framework of European Project Limit. Okay. The safety assessment service consists, the main idea is first to identify the requirement nanosafety service in order to address the needs of the company and their providers. Depending on the type of nanomaterials, the sector to which the product is addressed, for example, medical equipment, cosmetic, food, or whatever, and according to the stage of production developed, it is a manufacturing or production or it's a end-life product. Limit provides a wide set of service to client companies, their supplies, and the companies participating in the LEAP project. The service what are included in this safety assessment is first, physicochemical properties of the nanomaterials and or nano-enabled products. Also, the second, intended use along the supply chains and sector of use. The third service is eco and toxicological information, including toxicological and ecotoxicological studies. The fourth, the exposure data, including workplace, exposure monitoring data, and that I will really talk to you in the third talk for this open session. And to end, the process-related information and the regulatory issues. The workflow of this service go from the idea to the market. The phase 1 is making a safety request, and then we invite you to inform us and to fill up a questionnaire, and we have several meetings in order to know the type of nanomaterials, chemical identification, the physical state of your material, the production scale, the content, the intended use of this of your material, the sector, the safety data sheets if they are available, the toxicology and ecotoxicological data, it also is available. And in the second step, we go to all of this information we gather and we make a report, a pre-report for analysis of all of the data. The third step will be a diagnosis of this data, and that consists in two parts. The first part is a preliminary regulation analysis, which consists in making analysis of all of the product specified in these regulatory standards, and also in a specific regulation requirements. Then we go to a preliminary risk analysis, which consists in exposure potential to the worker and also to the consumer, if there is an end product, a hazard profiling, toxicological and ecotoxicological one, and to the end, the risk characterization. After then, we perform a completely report consisting in these three main branches. First, regulatory compliance analysis, what that consists in making a report on these regulatory requirements, barriers for placing the products on the market. The second report will be about risk issues, which include the toxicological profiling based on read-across approach and acute toxicological studies, and also in risk mitigation requirements analysis based on dustiness process containing and existing risk mitigation strategies. And to end, we perform and report in order to make a strategic planning. That consists in give an opinion for the expert to the client for the next steps to place the product on the market. Then ITENE has developed a platform which is with the companies that are interested in the safety assessment of the products can access freely and free of charge through the link that appears on the screen. In it, they will find information about the interest of carry out different analysis focused on guarantee the safety of their products, being in many cases necessary depending on the sector. The next slide is in this first window that appears when you access to the link. It is the landing page, which is divided into different sections which provide information of interest about the LIBIT project and the security pre-assessment related service offer. That information, go to the, you click in the project section. In the pre-safety assessment service section, we will provide a detailed information on safety service and gives an idea of the benefits of this service for the company. Then if you click the platform, the login windows appear. A login is required. To be able to access, you must be registered, and registration is free of charge. When you are inside of this platform, you have three different parts: the regulatory requirements, the defined product properties, and the nanosafety service. In the first one, the regulation, you have first to select is the nature of your material. Is a nanopore, the nanoformulation, the nanoproducts, then the type. There is 94 types of nanomaterial that you can choose in 12 categories. For example, if this material is oxide, nanoparticles, carbon nanoparticles, or metal nanoparticles. Then you have to select the sector for which this nanomaterial or nanoproduct will be going to be used. And then you have to specify the material. Different use-friendly and explain selectors, depending on the two sectors, will be appeared. And also in this, and then you have this window where displays regulation information relating to the selection of the previous step. Each field of the industrial branch provides information of regulation. Medical and events, for example, the regulatory requirements based on these inputs with downloadable documents and links. You also have a window where we can offer nanosafety service, sorry. And to the end, the third part of this platform, it is included to the product properties. And you can write the search properties, like, for example, at the example, we put zinc oxide. Then you have these key-table nanomaterials. All of the nanomaterials are in the databases. And it is displayed the physicochemical and the toxicological values. And then if you click the physicochemical information, you have all of the information available: the surface, specific super area, the endpoint, and also the toxicological information that is available. And to end, if you want to contact with us, at the moment it's not working, but it will work in the next weeks. You can send us a questionnaire about what is your demand, questions, or whatever. You can ask for your specific nanosafety related service. And yes, for that, with that, I will finish this part of the talk. Thank you very much for your attention. If you have further questions, you can make these questions at the end of the open session, or easily you can write me an email in order to ask everything. Thank you very much for your attention. I let you with my colleague Arantxa Ballesteros.
Hi everyone, this is Arantxa. Okay. Hi everyone, this is Arantxa Ballesteros. I'm project manager in toxicological and bioinformatics projects, and I will show you an overview of the regulatory compliance analysis that we in ITENE offer, and we have been working with this project of LIBIT. Sorry for that. Okay, this is the main content of the presentation. We will start with a contextualization of the the importance of perform or taking into account this regulatory analysis. Then we will see an overview of the main different regulations that apply to nanomaterials, and we will see the specific requirements that each legislation require depending of the sector of use. Then we will see the aim of this service, and we will finalize with some success cases and with the importance of the regulatory compliance in projected electronics. So to start with the contextualization, as you know, the nanotechnology and more particularly the nanotechnology-based products and materials have provided a huge potential for novel solutions in many challenges that we as society are facing. But as a result of their novel qualities and often new behavior, as opposed to the ordinary products or bulk products, there are also some questions about safety and how to evaluate the risk that we have to take into account. These are the main sectors in where nanomaterials are used. It goes to since biomedical and healthcare, renewable energy, also food packaging, processes, processing and agriculture, environmental remediation, and of course electronics and energy storage. So there is a huge wide of applications that nanomaterials are used, and we have to take in mind that we have to take all these legal requirements considered prior to place some product or some substance in the market. In the European Union, the nanomaterials are covered by the same regulatory framework that ensures the safe use of all chemicals and mixtures, which are the REACH and the CLP regulations. But due to their potential hazardous properties, these substances have to be properly assessed and their safe use needs to be ensured. So there are also specific provisions for nanomaterials in sector-specific legislation, such as, for example, food, biocide, or cosmetic regulation. Here there are an overview of the main regulations that applies to the most common sectors. As you can see, the general ones, which are REACH regulation and CLP regulation, which has a specific consideration for nanoform, but also we have, for example, the EMA on drugs, also cosmetics, biocidal products, food contact, or medical devices and advanced therapy medicinal products. Printed electronics is on this first general regulations. The framework that apply on this sector is decomposed by the REACH and the CLP, so we will see now more in detail what are the legal requirements. A new definition of nanomaterial is available since the last 10 of June. This is some progress because we have been, or the scientific community have been working in this new definition for the last years, and this is what is achieved. Nanomaterial means a natural, incidental, or manufactured material consisting of solid particles that are present either on their own or as identified constituent particles in aggregates or agglomerates, and where 50% or more of these particles in the number-based size distribution fulfill at least one of these three following conditions. The first one is one or more external dimensions of the particle are in the size range between 1 to 100 nanometer. The particle has an elongate shape such as rod, fiber, or tube, and where two external dimensions are smaller than 1 nanometer and the other dimension is larger than 100 nanometer. And the last one is that the particle has a plate-like shape, so where one external dimension is smaller than 1 nanometer and the other dimensions are larger than 100 nanometer. What are the specific requirements? Well, among all the possible regulations that can be applied to the nanomaterials or the nano-enabled products, depending on their sector of use, the REACH is the main one. This is the regulation on registration, evaluation, authorization, and restriction of chemicals and establishes the obligations for the European companies placing chemicals on the market, promoting the protection of health and the environment, and constitutes the main regulation applicable to nanomaterials nowadays. Several specific considerations are described in its annexes, and they should be considered by the manufacturing companies, but also by the importers, the downstream users, or the distributors. In detail, these are the specific considerations regarding the characterization of nanoforms or nanoforms assemblies subject to registration, which is described in Annex 6. Also, the chemical safety assessment, which is described in the first annex. Then regarding the registration information, which are described in Annexes 3 and Annexes 7 to 11. And of course, this is an important point, the obligations of the downstream users, which are described in the Annex 11. We offer these analysis services within the project through this part of the tool that my colleague Elena has explained a few moments ago. And this service aims to define the regulatory requirements to be considered to place the products in the market, and is intended to support the industry on the identification of the safety issues to be considered based on the current product safety regulation, also considering the environmental related regulations, and of course considering the current regulatory requirements on occupational safety health, and to guide support companies in the process of REACH registration, which is a very complex process. The service includes identification of the regulatory aspects to be considered prior to the placement of the product in the market, and more specifically in the case of the products or mixtures containing nanomaterials. Then regarding the REACH registration of nanomaterials for the companies within the European Union. The service includes also REACH substance registration, but of course QSER and in vitro testing, the development of the safety data sheets, and the chemical safety report that you as company have to present to the ICA, which is the official organism to deal with this registration process. And finally, CLP compliance, which include the development of the extended data sheets and the physicochemical characterization. Here we have some success cases in case that we have a company that wants to use some commercial material and want to avoid any legal problem regarding the safety of these ingredients or substances that they are using. We can perform in-depth analysis focusing on two sectors. This is the example for the first one on exposure-related information. We evaluate some specific endpoints regarding the exposure files, as for example exposure controls, in where we evaluate the information regarding the occupational exposure limits, which in the case of the nanomaterials are very limited, and also the derived non-effect level, which is a very important endpoint on exposure assessment. And here are the example for the analysis of toxicological information. Here we can see the different endpoints regarding the information focused on the effects on human health, but also on the environment. We can distinguish between, for example, acute oral, dermal, or inhalative toxicity, skin corrosion or irritation, also effects on eye damage or irritation, respiratory or skin sensitization, germ cell mutagenesis, and effects regarding, for example, carcinogenicity or reproductive toxicity. And regarding the toxicological information, well, more or less we have several organisms, bioindicators of the different matrices that we have to study and to present information. Also studies on persistence and degradability of the components, bioaccumulative potential, mobility to soil, or, for example, results of PVT. And why is this important in printed electronics? Well, because understanding and managing the complex and dynamic regulatory landscape of those nanotechnology-based products is very important to the business working at this cutting edge of novel materials and processes, as in the case of printed electronics, and because there is a need in the nanotechnology sector to minimize the barriers to market success and consumer acceptance, and ensuring the safety of products in that is, of course, a key element. And this is all for this part of regulatory analysis. I will give the floor back to my colleague Elena, which is going to explain more in detail the services related to occupational exposure assessment.
Thank you, Arantxa, for letting me the floor. I will explain now the standardization and safety service that we offer in the phase 3, and I will explain the risk assessment, the occupational exposure service. The content of my talk will be, I will give you a background about what is safety, the concept of chemical safety. Then I will explain the qualitative methods that there is to assess this risk, and I will finish to explain the quantitative information. I mean, how we can make and quantify what are the exposure for the worker or the user. The risk regulation establishes that the industry is responsible for ensuring that the substances that are manufactured, marketed, or used do not negatively affect human health and or the environment. Therefore, a risk assessment is necessary for all of these substances. In amounts greater than 10 tons per year, where the conditions that are considered safe to manufacture and use a substance are identified and described. There is two phases. There is 3 phases. One is a perform a full hazard assessment based on the physicochemical toxicology and ecotoxicological properties of the substance in any size, shape, or physical state. Then we will do a exposure assessment, defining the exposure levels and the reasonable condition of use. And in the third place, we go to a characterization of the risk by comparing exposure levels and threshold below which risks to human health and environment are considered controlled. This characterization of the risk it gives us a number equal, less than, or equal to 1, which are greater than 1 that is an acceptable risk. Then in this framework, if the risk characterization ratio is less than or equal to 1, the risk will be under control, and therefore the chemical safety assessment ends here. If the risks are not under control, I mean this assessment is greater than 1, the assessment needs to be refined either by obtaining more data on the properties of the substance, by changing the conditions of manufacturing of use, or by making more precise exposure estimation. The process is interactive and will continue under the risk and so to be under control. Life cycle analysis is very useful in defining potential risk to workers or consumers and the environment, as it provides us a holistic view of the impact of nanomaterials from production through use and final to disposal. In a comprehensive risk assessment or life cycle assessment, a life cycle framework is the necessary starting point for building exposure scenarios and studying the processes and mechanisms that lead to safety problems. Understanding an exposure scenario as a set of information that describes the conditions under which the risk associated with the identified uses of a substance, either it is a pure state or a mixture. Therefore, it is important to consider not only the consumer use, but also the entire life cycle product. Well, to start talking about risk characterization method, it is important to point out that when it comes to nanomaterials, the main difference is that with a qualitative evaluation, we will not obtain a risk characterization rating. Here, due to the lack of limits such as DNL, derived no effect level, and the ITENE, predicted no effect concentration, and the lack of personal sampling equipment. Therefore, other qualitative methodologies such as control branding will be applied always, providing a strong and consistent justification to support the conclusions that the operation conditions and risk management measures described in the special scenarios are sufficient to avoid the probability of adverse effect. This rationally consists of providing modeling approach to estimate exposure and complete an overview of risk characterization throughout all relevant life cycle stages. However, the selection exposure determined must be relevant to the route of exposure considered, whether through inhalation, ingestion, or dermal contact. This is a comparison between these control branding tools. Here we can see a comparison between the most commonly used qualitative models for risk assessment, showing the relationship with the different assessment indicators. The nanosafety, it is low or high. And evaluative substance power liquid solid validation, the tool is validated by documents that contain independent data and can be more precise. Decisions regarding nanometric particle size, reliability of hazard classification, exposure classification, and will give us orientation guides to minimize this risk. This analysis demonstrates that the scope of substance assist methodologic principles of these control branding tools it is needed. We have examined use that the need for a careful selection of these control branding evaluations tools, depending on the scenarios to evaluate. Because we have to take care about which is the data that we keep inside of these evaluations tools, because the same scenario, if you put different size or different natura of your nanomaterials, could be different risk assessment. Here you can see this is the output of the information that you have to click and to input the parameters. Since if we score the results obtained in the previous radar diagram, we see that the nano tool, nanosafer, and Stoffmeyer nano tools have a great comprehensive advantage over the others. These three tools are the ones that we obtain the most successful results, and these results can be compared with each other. In this table, we can see the necessary input parameters requested by these tools. First, they focus on information related to the substance, such as physicochemical properties and the state of matter. Then, in the information related to the process, a detailed description to define the scenario. And also the quantity uses, duration, frequency, energy, and emission of respiratory dust. It is also asked for information related to the workplace, such as the number of workers, the rate of air exchange, cleaning, and maintenance operation. We see that this section is covered much more by the Stoffmeyer tools. Clearly, it asks us for information regarding collective or individual protection. In this table, we see a comparison of the results obtained by the three tools of the same spatial scenarios, among which are the packing and driving of calcium carbonate, feeding of iron oxide to a reactor, for example, and the separation of iron oxide. Here we saw the quantitative difference in the accuracy of the spatial classification between different tools. In this case, the free tools giving us a risk band rating close to 1. You can see in this column, the exposure band ratio and the risk band ratio, and also the preventive measures. What differs a little more it is in a relation to preventive measurements, since it is here when the nanosafety tool is much more detailed. Depending on the scenario and the materials, we can see which tools it is better for your application. It is important to make a assessment of the comparison between the three tools for each scenario. Here we see an example of how the nanosafe tool generates the risk assessment report. In this, we can see in detail the results, time, and the input data used for the calculation. Now we start the second part of the talk. I will talk now about the exposition in the workplace to what is necessary to perform quantitative risk assessment. The part I explained before was about the qualitative assessment, and then we start with the experimental part, with this quantification, which is the exposure in the workplace. First of all, we detail the exposure of the worker, if it is a risk or not, for the previous results. The risk of nanomaterials are linked to three potential routes exposure of the workplace: inhalation, dermal contact, and ingestion. This last one have less significance. The recent literature review have concluded that there are very few data on occupational exposure to nanoparticles. They aggregate or agglomerate, and the existing data show high variability to the application of non-standard methods in the measurement. So that's how we always recommend to use to quantify this exposure assessment, make through a standard method. And also, the lack of robust and comparable toxicological data has limited the publication of occupational exposure limits to data. However, they are recommending certain exposure values. In this slide, we can see the equipment that we can have, and which is the input data that we obtain when we make an assessment or the exposure of scenario of in the workplace. The equipment recommended in the methodologies established by the OK and the other organizations are usually classified based on physical operation principle and metric measurements variables. The physical principle will be optical, we have a laser, electrical, or gravimetric. And the output variables that we have is numerical concentration of particles, size distribution in nanometers, mean geometric diameters, mass distribution, and surface area. Here we can see the different kind of technologies that the market can offer us at the moment. For one is the portable device. This is a small one that we can go and make the assessment in situ in the workplace. And normally these are divided in two parts. One is in principle in particle counter by condensation, and the material that needed to condensate these particles will be water, ethanol, or butanol. And also, the other kind of device are a particle counter based on electrical charge principle. An example of that are the mini or nanotracer. In the second column, we have the transportable device, which are classified by the mean of electrostatic. And it is, for example, the SMPS, the scanning mobility particle size, the ITENE, the fast mobility particle size, and EP, surface area monitor. Then we go to sample. That sample means that we, with a pump, we capture air for the atmosphere of the worker, and there is, and then we make analysis of these particles that we have capped in the air, but based on element oscillating microbalance, quartz crystal microbalance, or MODI and nano-MODI impact factors. At the last point, we use the gravimetric analysis, and then we put our sample in order to cap this air with pumps and filters in specific sites to control and to analyze the hotspot. Also, normally we put for the worker also a personal sample in order to collect this air that is in the brain zone of the worker. In the next slide, we can see the size of nanomaterials and also the price of the device that are analyze this exposure. We can see that the potential risks first for the material increase when the size decrease. I mean the hot risk, the main potential risk is below 1 micrometers in the range of nanometers. Also, we can see that this setup to measure and the device to measure and inform which is the concentration and the size of the nanomaterials that is in the atmosphere increase as well when we go down in the scale. Then, when we have explained which is the device that you use to make this evaluation, we explain now the methodology, which is the methodology that we follow to make this assessment evaluation. We follow a methodology of tier level that go from tier level 1, 2, and 3. That we follow this tier level is the more common methodology that are using for this, and recommend the National Institute of Occupational Safety and Health and the Organization of Economic Cooperation and Development. The first step, when we are in the tier 1, we make first an evaluation. We send to the industrial partner the questionnaire to gather all of the important information of the process that we want to make this evaluation assessment, and also to identification of the emission source, the definition of measure strategies, to know which is the background analysis and which are the data processing and reporting. That is the last step. The first stage in the risk assessment process focus in gathering information, as I explained before, identify the emission source, and determine the types of process, material characterization, and work practice. After we receive this questionnaire, we organize an online meeting with the industrial responsible of the company in order to check all of this information. When we know that there is a risk, also helped by the qualitative analysis, the nanosafe, Stormmeyer and Nano, we go to the second step. The second step focuses on the definition of a sampling strategy based on the information obtained through questionnaires or direct interviews. According to the working groups of the European Nanosafety Cluster, the strategy to be defined will include the definition of the sampling points, the duration of this sample collecting samples, and the methods and units measured and the units method used. The main strategy that we will follow is first planning the scope and the definition of the strategy, and in the second place, selection of this metering equipment, the equipment that I explained in the previous slides. And then we go to this, that is the name of this second level, the tier 2 and 3 levels. Here we can see what is the information that we can gather in the level of tier 2, the basic protocols. First, we measure the background, that is the concentration of particles in the air before the process starts, with a counter particle condensation that we can follow here. You see, for example, these both lines that when the system is off, there is a very small concentration of particles in the air, and when the process starts, we go with a sharp jump to a concentration of particles in the atmosphere. Here we can also see an analysis of these nanoparticles that we have collected in our filters and we can perform a scanning optical microscopy analysis and also a chemical analysis by ERAX technique. Then we have to interpret the data. When the risk stays, we go first to the level tier 3 approach. Then, as I said before, when there is with the tier 2, we have evidence of exposure with analysis of the concentration of nanomaterials with the CPC and plus the microscopy. Then we go to this, we go to have more information with more sophisticated treatment. Then, for example, you can see here, as I told before, we have this MPS, the aerodynamical particle size, and other more sophisticated treatment. This graphic here, this three-dimensional graphic, is the output of our SMPS, that is our ITENE labs. And we can see here, for example, in this axis, the particle concentration, the number of particle concentration. Here in the x-axis, we can see the time, the evolution of the time, before from the background, the process, when the process starts, and the evolution of the process. And in this third axis, we can see the size distribution of the particles that it is in the atmosphere. And it is an important data, because not only we know we have with a simple view a complete picture of the process, we also have how is the dynamical of these particles aggregation and how many times it stayed in the atmosphere. For example, before we make an exposure assessment, we delimitate the scenarios, each of the scenarios. We put here, for example, this is a process about dispersion of oxygen graphene in aqueous solution. We name the scenario with description of which is the task that can be completed one of two of these types, and also the contribute scenario. That means these tasks are making one for the other one. We can make that this is the contributed scenarios. Also, the duration of the activity, the general ventilation, and the EPIs usage. We can, that is the output. We can see the background measurements and also the evaluation of the different process here. And also important point is we always measure two different size. The size, it is more in the nanoscale range, from 10 nanometers to 300 nanometers. And also the concentration and the size distribution of the higher particles. The particles are compressed between the size from 300 nanometers to 10 nanometers. And in this graphic, we can see, for example, in a simple view, we compare which is the concentration of the materials, and which is the scale, the size scale, as we are talking. And also we compare the concentration of that we have measured during the background, and also that is the blue one, and during the process. And then we can see the difference, and we can assess what is the risk. If for example, the level of the concentration of the nanomaterials is 3 times higher than the background, we can assess a very high risk. And to end this campaign, we make an execute analysis of, as I told before, by scanning optical microscopy. And we can see here with this analysis, the scope of the analysis is first to know which is the concentration of the materials, which is the chemical composition in order to assess which is the risk. And also, what are the particles? For example, here in the picture, we can see that we have a very aggregate of a lot of nanomaterials, and we see that we have in this picture carbon oxide, manganese, titanium. That means that during the time that it is sampling the process, we catch the nanomaterials are being aggregated in higher nanomaterials. No? And for example, we also perform more sophisticated techniques like the transmission electron microscopy when we want to know, in order to assess or evaluate the risk, if these materials or nanomaterials are crystalline or not. Then this reason we use ITENE, and then we can see that is an example picture. We can see, for example, here in this picture that there is an overview of the filter, and also we can see here that in this case are graphene, and we can observe that we in the air in this company was graphene oxide and conglomerated with other metals in air, and that is a very high risk assessment. Okay, and to finish this part, I will also to explain the technological solution developed by ITENE to face current challenges. We have to start explaining that according to the ECHA, the European Agency for Chemical Substance and Mixture, from 1st of January of 2021, it's mandatory to provide information on the nanoform in the safety data sheets of all products. Within this information, the index data can be included, which is a crucial input parameter for the control branding tools that we have explained before. And for this purpose, this setup is the small rotating drum method. It's been developed in ITENE based on this standard, and this one, which the information that this method gives us is the power for evaluate its sustenance by this rotating valve. These sustenance measurements and characterization provide users with information of the potential for dust emissions. Bulk material is handled or processes in workplace. The output of this method will be the dustiness index that, as I said before, is essential, this data, in order to have a qualitative control branding process, in order to use these tools. Also, we give us information about the particle emission rate, collection of particles, and also we collect particles, and we make in the respirable function, we observe this analysis by an electron microscopy. And with that, I will finish this part of the talk. I will thank you. And now, again, if you have a further question, please write the mail, or you can make the questions in the end of the open session. And now I give the floor to my colleague, Arantxa Ballesteros. Thank you very much.
Okay, thank you, Elena. Now, sorry for that, I have to go through my slides. Now it's the time to explain, sorry, I have been very, okay. Now is the time to explain more in detail the services regarding the ecotoxicological profiling studies. So we have to start with the challenges in the nanotechnology. Then we will see the legal requirements to consider when we assess toxicology. And we will see the methods for the safety assessment of nanomaterials. And we will end, as I previously said, with success cases. We have started. So to understand the importance of the toxicological profiling services, when we are focused on nanomaterials, it is interesting to know why they are particular challenge in the nanotoxicology file. So the main reasons, or the main reason, is that due to the characteristics of these materials in nanoscale, compared to the bulk materials, we have to keep in mind some questions. For this, we will go back to the definition of nanomaterials that I have already described. And the first complexity lies in the fact that Within the umbrella of the definition of nanomaterial, there are numerous forms in which they can be presented, such as, for example, nanofibers, nanoplates, nanoparticles, nanocomposites, fluid nanodispersions, or nanostructured surfaces. And depending on the form of these materials, we have to take in mind some limitations and some particularly methods to perform when we work with them. So to look at this in a little more detail, let's divide these nanotoxicology related challenges into 3 different sections. The first one is related with the physicochemical characteristics. Although they have the same chemical composition as the non-nanoscale substances, they may have a different behavior and more different properties. So we have to take into this in mind. And this is also closely related to the next challenge regarding the toxicity. Precisely because of their different properties, as for example, a higher specific surface area, more reactivity, a smaller size, or solubility, they may have toxicological effects on both human health and environment, and we have to assess these potential effects and try to ensure the safe use of these materials. The last one is related to the lack of standardized procedures for the assessment. There are several reasons for the lack of international standardized and common procedures for the risk assessment of nanomaterials. On the one hand, the absence of epidemiological and toxicokinetic data, which will provide information on long-term health effects as well as on the process occurring in the body from the entry to the excretion of these nanomaterials. Also, on the other hand, the lack of widely reproducible in vitro methods, as the variability in the characteristics and behavior of these nanomaterials are very high. And this is also due to their low solubility, especially in aqueous matrices, which makes it difficult to make them compatible with the usual culture media used in toxicological and ecotoxicological studies. And in their work generally, we have to use carriers that allow an homogeneous dissolution or dissipation of these compounds, because we found several restrictions and limitations on that. The complex composition of the culture media, especially the cell culture media, hinders the stability of the nanomaterials solutions. Also, the behavior in aqueous media is not constant, and this is directly related to the variability that occurs in the viability of the sample during the assay, which at the end affects the exposure during the tests, and also to its high potential for bioaccumulation. In relation to exposure, it is also affected by the agglomeration and sedimentation processes to which nanomaterials are prone. And finally, as a consequence of the above, their effects does not always follow the dose response principle. The applicability of the OECD methods to the study of these nanomaterials is under continuous revision, and exist some recommendations and guidelines based on standard procedures which has been generated by the scientific community. Well, in addition to the challenges in nanotoxicology, it is the case that, as we have seen above in the presentation on legislation, there are some specific requirements when it comes to assessing the properties of nanomaterials and submitting information about them to the official bodies, like, for example, ECA. And in detail, we will look at the requirements for the nanomaterials in nanoform in the main regulations that apply here. The first one and the main one is the rates. Here, there are some general provisions for the substance evaluation, and we have to present specific information regarding physicochemical properties and toxicological information. And also the important point on general rules for the downstream users when they deal with nanomaterials. On the biocides regulation, for active substances in nanoform, companies should to prepare a separate dossier on that substances. Regarding CLP and cosmetics, it is a need that the list of ingredients must show the presence of a nanomaterial when applied, and the non-nanometric and nanometric forms will be assessed separately if the nanomaterial has an active role on the product. Regarding the EFSA of food contact materials, only those nanomaterials included in the list of authorized substances may be used, and the assessment and also the authorization is done on a case-by-case approach. And finally, regarding the medical devices and the advanced medical therapies, here the degree of evaluation required depends on the likelihood of the nanomaterial release from the device which is used. Well, with all this information in mind, it is therefore time to know exactly what are the objectives of these services that we offer to assess the potential effects of the nanomaterials. These services aims to assess a potential both on human health and environment, and they are needed to place a new product on the market in compliance with the legislation, and also, of course, to know the risk posed by a material in order to be able to adopt the necessary precautionary measures during its handling or use. The service aims to conduct a comprehensive study on ecotoxicological and toxicological properties, and it's carried out considering the endpoints of interest depending on the sector of use. Here is an overview of the main assays we perform linked to the cell lines and the organisms we use, as well as the main regulations that apply in each case, but we will look at them in more detail below. So we will start with the methods for assess the effects on human health by in vitro test. We use human cell cultures that replicate the behavior of the cells at cellular level and provide useful information without the need to use in vivo methods, which, as you know, are more costly and ethically problematic. So, depending on the most likely route of the entry into the organisms for a particle, the cell culture to be used is selected depending on, for the inhalation route, we will use the A549 cell line, which is from the alveolar epithelial cells. Then for dermal contact, we use the Hackett cell line, which is from skin keratinocytes. And if we want to assess the effect by oral route, we will use the CACO2 cell line from colorectal epithelium. Okay, in all these cell cultures, several effects are studied. The first one is cytotoxicity, which is an alteration of the basic cellular functions. And we study this effect by the MTT-assay. Then the genotoxicity, or the study on adverse biological effects on genetic material. We will perform this through the COMET assay. And in addition to that, we can also study the irritation and inflammation reactions, which are the effects induced in response to inflammatory or stress reactions. And we will perform this through immunotoxicity test. So we will look now in a little more detail at what each of these services consist of. So with regard to the in vitro studies, and the first one, the cytotoxicity assay, is the most common assay to study the effect on cell viability. Here we perform an exposure of 24 hours to the sample, and its principle is a colorimetric test, which is based on the metabolic reduction of the MTT salt. We use 96 well plates, study different concentrations, 5 different concentrations. So we rate or measure the effect by an spectrophotometer. We read the optical density in a wavelength of 590 or until the 620. And the results obtained allow to know the percentage of inhibition of cell growth and the dose response representation for each sample or particle. And the biological endpoints that we study are is the effective concentration 50, which is the concentration that produces some effect on the 50% of the population which is exposed, and it is calculated by a probability regression. And this result is used to classify the damage as extremely toxic, very toxic, toxic, of concern, or non-toxic. Then we have the genotoxicity study. We perform the COMET assay. In this case, the aim is to study the damage to the nuclear structure of the cell. So it's based on a cell electrophoresis method in where the DNA fragments produced after the material break migrates in an electric file. And for the reading, the genetic materials is fluorescently labeled, and the migrated material is observed using a fluorescence microscope. And then we perform some statistical analysis using some analysis software. And the results obtained allow to know the percentage of the DNA damage. So here the endpoint constitute the percentage of DNA in the tail, and is used to classify the damage as high, medium, low, or null. As a test, complementary test of these the last two ones, we also can perform some studies on irritation and inflammation reactions, and the aim is to study the response to inflammatory or stress episodes. So here we have the most common two methods, which are the ELISA one and the Rose determination. This is very interesting. The reactive oxygen species are a series of molecules that can be produced by pathological or non-pathological situations. And when these species are produced in large quantities in the intracellular compartments, are an indicator that the oxidative stress situation is occurring and it is affecting the cells. Not only the assessment of the potential impacts on the human health is important, but it is also essential to assess the potential impact on the environmental organisms. So for a screening type of study, it is usually common to work with two different organisms, which are bioindicators of the aquatic ecosystem quality. And the effects study are the mobility inhibition in the case of Daphnia and the inhibition in the growth in the case of algae. In more detail, this is the in what the acute immobilization test on Daphnia consists of. We expose the organisms 24 hours and 48 hours, following the OECD guideline for that, testing 5 different concentrations, and we aim to determine the effective concentration at 24 and 84 hours, and we see how the sample of a study affects to the mobilization of the organisms. Then this is the algae one. Here the exposure is on 72 hours. Also we perform or test 5 different concentrations. Here the effect is read by an spectrophotometer. And again, the biological endpoint determined is the effective concentration measured at the 72 hours. Apart from the in vitro or bioassays studies, there are also other tools or approaches for the study of ecotoxicological and toxicological properties which are available and should be used whenever and wherever it is possible, because these approaches aims to minimize the animal experiments as much as possible, and are strongly promoted by the European Commission. The first one are the integrated approaches to testing and assessment. They really rely on the existing information for the chemical hazard characterization and use apart from the experimental available information, also QSAR, redox, or other in silico tools, and aim to use the existing toxicological information in combination with these in silico techniques in order to minimize the number of tests needed to ensure the safety. Then we have the adverse outcome pathway, which is a recent approach for risk assessment, and it considers the complexity of the interactions, process, events, and relationships that occur at the organism's level, in not just in a cellular level. And then we have the computational methods, which are an alternative to the animal testing, are based on mathematical approaches through we can predict potential effects that a substance or a mixture can cause, and there is no need for experimental study in that. Finally, let's look at some real examples of toxic properties. In this case, I will show you two studies which are focused on the study on health effects. Here in the first slide, I show you the results we have achieved for a sample with a carbon-based product. The studies were conducted considering the three main routes, which are the inhalation, oral, and dermal route. So in these figures, you can see the results of the cell viability study for the three cell lines. The percentage viability for each of the 5 concentrations tested plus the control is shown, and it can be clearly seen that there is a dose-response relationship in this case, in which the greater amount of sample we use, the greater effect on the cell viability. In summary, the results show that the substance has no effect on the cell line corresponding to the inhalation route, but in the case of oral and dermal, we have observed some effects as the EC50 are below the 100 ppm, which is the limit. In this case, the results are for the genotoxicity study. The images are taken from the fluorescence microscope, and the image on the left show the appearance of the control, in which you can observe dense dots indicated that the nucleus is intact, while in the image on the left, we can see displays genetic materials indicated that the cell nucleus has been ruptured by the effect of the sample. So in this case, the cell lines in which the most damage is observed are those corresponding to the oral and the inhalation. This is just like an example of what are the results. Why is this important? Okay, we will conclude by looking at the reasons of that. First, to know the toxicological properties relating to the potential effect on human health, and of course, the effect on the environment, considering different environmental matrices like soil, aquatic environments, or air. To have broad experimental toxicological information in order to be able to make a comprehensive risk assessment, also considering the information provided by the occupational exposure assessment, to comply with the applicable legal requirements for marketing a nanoform product in the market, and of course, because knowing this information is key to ensuring the appropriate personal protection and risk mitigation and control measures that we have to apply in a place when we handle with these materials. So this is all from my side for this last presentation. I think that we are running out of time, so maybe it is better if you can address your questions to via mail for us, and we will be happy to answer them. And thank you very much for attending this open session on safety services. We hope that you have enjoyed the presentations and some useful information has been shown with you, and of course we are able to or happy to answer your comments, suggestions, or doubts. So thank you very much to all of you.